Okay, so cracking. Longer chain hydrocarbons, they come from fractional distillation. They're not that useful, so what we do is we use high temperatures, pressures, and catalysts to break them up into smaller molecules which are more useful. This is the process of cracking. So if I take, for example, heptane, heptane's got 7 carbons, count them. Then we take this long hydrocarbon and cracking. One possible process here is that it breaks up into ethene and an alkane. 1, 2, 3, 4, 5. Which alkane would that be? That would be pentane. You are right. I hope. Pentane. Okay? This is just one possibility. Now notice we get now a molecule with a carbon-carbon double bond, an alkene. We'll talk more about them later. Ethene, because there's 2 carbons. And we get the rest in this molecule. They're all single bonds, so that's an alkane. This is one possibility. We could have got propene and butane. As long as the same number of carbons exist in the products, we're fine. When small alkanes are cracked, when they're broken up, for example ethane, there's not a lot to do. So what can happen is ethane, if we crack it, can be broken up into ethene and hydrogen. Something for you to know. That's the overview of cracking. Have a look at the pages indicated, answer the questions, read the text, just to give you a bit of an idea. What's the point of cracking? Let's just remind ourselves. We're taking longer, less useful alkanes, and we're making smaller, more useful alkanes and alkenes. Right, let's move on to homologous series. Now basically homologous series are families, and they're similar organic molecules with the same functional group. Now the functional group is the business end of the molecule. It's the thing that actually does the reacting. Okay, you'll get a feel for that as we go through these. They have the same general formula. We'll look at the general formulas. Similar chemical properties, because it can change slightly as the length of the carbon chain changes. They have gradually changing physical properties. Melting points, boiling points will slowly increase as the chain gets longer. And we're going to look at the following: the alkanes, the alkenes, the alcohols, and carboxylic acid. Those are the 4 functional groups. Sorry, those are the 4 homologous series that we're going to talk about. Right, this is just a general overview, so stop me here, have a look at those pages and answer the questions, just to get a bit of a background feeling for this part of the course. Right, let's start with the alkanes. The alkanes, they're hydrocarbons joined by single covalent bonds, so single carbon-carbon or carbon-hydrogen covalent bonds. If you look at these numbers, if you like maths, you look at these numbers, you can see that there's a relationship between the number after the carbon and the number after the hydrogen. And that relationship gives us the general formula of alkanes. If you want to take a minute and try and work out what the relationship is. And it is CnH2n plus 2. So if I take, for example, butane, Cn, 4 is the N. If I multiply 4 by 2 and add 2, I get 10. Okay, that's the alkane's general formula. Have a go drawing the structural formula for butane and octane, just to get a bit of practice in. It's not difficult. And there you go, nice and straightforward. Make sure everything gets single bonds. Now, something you can do is find the boiling point for the first 10 alkanes, and you can add them to this table. Okay, you can also indicate whether they're solids, liquids, and gases at room temperature. Something to bear in mind, and we saw this with the halogens, the longer the chains, the stronger the intermolecular forces. So the bigger the molecules, the stronger the intermolecular forces. And that makes the melting points and boiling points go up. So longer chains, stronger intermolecular forces. Right, now, alkanes, they're not that useful in chemical reactions, but they do three things. There are three types of reactions you must know, but they're still relatively quite unreactive. They will burn, which is why they're great fuels. And if they burn with lots of oxygen, we call it complete combustion, and you get carbon dioxide and water. Okay? With limited oxygen, you get carbon monoxide and even carbon, soot, can be produced. So have a go at the complete and incomplete combustion of pentane. There you go, I've done it for you. You can see here, hopefully all of my balancing is correct, but you can go through and check it. But essentially here with plenty of oxygen, 8 moles of oxygen, you get carbon dioxide. 11/2 is 5.5 moles of oxygen, you get carbon monoxide. 3 moles of oxygen, you get soot. But in reality, if you had relatively limited oxygen, you'd get a mixture of all of these things. Combustion is exothermic, we said that before, and that's why these are used as fuels. Natural gas, which is mainly methane, is used in the home. Butane and propane, they're used as camping gases, and octane and diesel in vehicles. You need to remember these uses. The next reaction of the alkanes is substitution reactions. Now these are actually, you'll remember from year 10, photochemical reactions. Methane and chlorine are actually explosive. You have to be very careful with it, okay? And it's light, ultraviolet light, that can initiate the reaction. So in UV light, the equations, which you should remember, are that. There's a series of equations. The chlorine reacts with the methane to produce chloromethane and HCl. The chloromethane reacts with more chlorine to make dichloromethane and HCl. Dichloro plus chlorine, trichloromethane, and trichloro plus chlorine, tetrachloromethane and HCl. So lots of HCl, lots of different products, and that's a bit of a problem really. The final mixture is a big mess of all of these products. So substitution reactions give multiple products, which means they're not a good way to make a specific compound. How would we separate the products from this type of reaction? At the end of this, how would we separate the different components? I hope you remembered, we'd use fractional distillation, wouldn't we? Because they have different boiling points. What's the third type of reaction that alkanes undergo that we've seen already? For combustion, substitution, and the third one is cracking. We saw cracking previously, didn't we? And that technically is a reaction that they do. Okay, essential chemistry, some pages and questions for you. Isomers. Structural isomers are molecules with the same molecular formula and different structural formula. Okay, great. So molecular formula is the actual relationship between the atoms present, isn't it? So you've got 5 carbons and 12 hydrogens in pentane. And we could classically draw it like that. Straight chain, pentane. But there's another way of arranging 5 carbons and 12 hydrogens that has the same number of hydrogens and carbons, but a different structure. There you go. If you look at the valencies and you look at everything, all of the bonds, everything's satisfied. And there's even another way, and it's that. So these are all different arrangements of the same stuff. So they've got the same molecular formula, but different structural formula. Okay? And that's called isomerism. And these are isomers. You might want to think about how you might name them, but don't worry, that's not really IGCSE. Have a look at the pages on essential chemistry. There's quite a few pages to work through there and answer any questions. Again, a lot of this is just background, just general knowledge about organics. Alkenes. So we've done alkanes. Alkanes were hydrocarbons with single carbon-carbon and carbon-hydrogen bonds. Alkenes are slightly different. They're more reactive hydrocarbons because they contain a carbon-carbon double bond. We made them by cracking, remember? So you might want, mathematically, if you look at this, you might want to just make sure you see that the number of carbons and the number of hydrogens has a very simple relationship, doesn't it? There it is. Okay, the first few, well, actually not the first few, are they? Because, oh no, they are, yes. Ethene, propene, butene, and pentene would be the first 4 alkenes, because we can't have methane because you need a carbon-carbon double bond. So they start from ethene. Just as a bit of practice, draw the structural formulae for hexene. It says formulae, but it should say formula. The full structural formula for hexene. Have a go. And there you go. That's one possibility. Now, the astute amongst you will realize that you could have put the carbon-carbon double bond somewhere else. So this is just one possibility for hexene, isn't it? How about butene? Well, this takes into account the different possibilities now. Now, what was the name given to molecules with the same molecular formula but different structural formulae? They were called isomers. So these are the structural isomers of butene. Okay, you can see you can put the carbon-carbon double bond at the end or in the middle, or at the end and then with a little side chain here. Names, you may be asked some of these names. Butanene, because you number from the end closest to the double bond. So this would be number 1 carbon, this would be number 2 carbon. And then you put the smallest number associated with the double bond. So butanene tells us that it's next to the first carbon. Butuene, first carbon, second carbon, butuene. And this is only 3 carbons in a row, so it's a propene. And it's got a methyl group on the second carbon. So it's 2-methyl prop 1-ene. Now I would argue you don't have to have that one because it couldn't go anywhere else. So it would be 2-methyl propene. Those are the 3 basic structural isomers of butene. Nota bene. Alkenes are called unsaturated molecules as they contain a carbon-carbon double bond. Alkanes are considered to be saturated. So it means they're unsaturated so you can do something with this carbon-carbon double bond. You can do lots of things because alkenes are quite reactive. they undergo addition reactions. So what you typically do is you add things to the double bond. Now, alkenes will burn. They typically burn with a yellow flame because of incomplete combustion, but they're not used as fuels because they're more valuable in other reactions. So interesting reactions. The first one is a test for unsaturation. So we use this to test to see if we've got an unsaturated molecule. Or, put it in another way, we can use it in this context to test if we've got an alkene. So question, have I got an alkene? I get some bromine water, which is a kind of yellow colour, and it loses its colour to become colourless. So decolorization of bromine from yellow or brown to colourless. So ethene plus bromine water, this is what happens. Ethylene is the old-fashioned name for ethene. Ethene plus bromine, the bromines attached to the double bond, one on one side and one on the other. This is called 1,2-dibromoethane. It's now an ethane again because there's no double bond. And this is colourless. So this is the test for alkenes. The bromine water turns colourless. Okay. We say the bromine is added to the double bond. It's an addition reaction. With hydrogen and a nickel catalyst, now the temperatures here vary according to the textbook. I think your textbook says 60 degrees. Many textbooks say 170, 180. As long as you give a temperature in that range, that'll be fine. And a nickel catalyst. The hydrogen adds to the double bond. So for example, if I add hydrogen to ethene, then I get ethane. Not really a very useful reaction, is it, in that case? Because you're taking something that's really reactive and useful, and you're making something that you can get from fractional distillation of crude oil really easily. So you wouldn't do this reaction, but it is a reaction to have in your toolbox. Why? Because you can play around with a number of carbon-carbon double bonds in a molecule, and this was used to make unsaturated vegetable oils, like sunflower oil, for example. If you make some of the double bonds, single bonds, using hydrogen, you can make it into margarine. So you increase its melting point. Okay, so it's used in the production of margarine, this particular reaction. It's often called hydrogenation. Hydrogenation. You might see that somewhere. Hydrogenation. If you use steam with this is a phosphoric acid, H3PO4 is phosphoric acid catalyst, 300 degrees and 70 atmospheres pressure, quite a lot of pressure, you get an alcohol. So ethene plus water, what you get is the hydrogen attaches to one side of the bond, the double bond, and the OH attaches to the other, and you get ethanol. Okay, so to make alcohols from alkenes, we use steam, phosphoric acid, high temperature, and pressure. Unfortunately, you need to know these reactions, so get learning. And the fourth reaction, and almost discovered accidentally, but very, very significant in the last 100 years, is polymerization. Alkenes join together to form long chains. This is called polymerization. So if I take ethene at high temperature and pressure and an oxygen catalyst, then it does this. The ethene molecules, we call them monomers, one part, mono, one mer part. We take lots and lots of monomers, the N means big number, and we make them join together to make a long chain, and that's called the polymer. This is ethene, so the polymer is called polyethene. Polythene. You can abbreviate this as this, using square brackets, all very important. This bond has to cross the bracket, so you show that this continues in space, and you put the little n down here. So the number of molecules you started with go into a long chain. That's called the repeat unit or the repeating unit. Okay? Polymerization. These are synthetic polymers. We're making polymers. Uses of polyethylene, plastic bags, bottles, bins, kettles. There are too many uses, and that's a problem, isn't it, nowadays? Very useful material, but we've tended to abuse it. This is called addition polymerization because you're adding lots of monomers together to form the polymer. And remember, alkenes undergo addition reactions. So you're kind of adding all of these molecules, you're lining them all up to make this long chain. Notice there's nothing lost. Everything from the monomers goes into the polymer. Okay, basically this double bond breaks and forms two bonds either side. There are lots of examples. We'll mention a few now. Propene. Propene looks like this. Look, we've drawn it in a slightly different way. Look, you've got the CH3 coming off the side. So you keep these, you've got your double bond here, keep these things in the right position, and that forms polypropene. Okay. Chloroethene looks like this, and it forms polychloroethene, which you used to call PVC. We still do. The reason why it's called PVC is because this molecule didn't used to be called chloroethene. It used to be called vinyl chloride. So polyvinyl chloride is PVC. Now I'll let you look up uses of these things. Propene is used in lots of things, for making crates, for making ropes. Polypropene, sorry, not propene. Making crates, making ropes. PVC is used for making tiles, making pipes, making clothes, lots of things. Have a look. Phenylethene is this funny little thing with this like Mercedes-Benz symbol on the outside. Again, look, you've got the double bond and they break to make this is polyethene. Sorry, this is phenylethene. This is a phenyl group. Phenylethene. So what you get is polyphenylethene, which was given the name polystyrene. You can look up uses of that. And tetrafluoroethene, that's an ethene with 4 fluorines, tetrafluoroethene. Remember, ethylene is the old-fashioned name for ethene. So tetrafluoroethene, when they come together, you get polytetrafluoroethene, PTFE, sometimes called Teflon. Teflon's got some interesting uses too. We really couldn't survive without polymers, but we need to start to think about how we use them and how we dispose of them, obviously. Now that's what you're going to do now on your own time. Read the page. I'll read page 237. Think about the following. What's the problem with disposing of polymers? What can be done to overcome the problem? We'll talk about this a bit further on too. But you need to start to think about the environmental problems caused by polymers. There's a podcast, or there's 3 podcasts on plastics on the website. Have a look. When you click onto this first page, if you scroll down that first page, there's lots of podcasts, and the ones on plastics are clearly indicated. And there's several pages for you to look at in Essential Chemistry. Okay, read through them carefully and do the questions.